Okay, continuing with this theme of strain energy, potential energy, total energy, we're going to move on to Castigliano's theorem. Now, Castigliano's theorem, there's two theorems, but I'm only going to talk about the second one here because it's more relevant to solving the problems that might be on the final. But anyways, okay, so Castigliano's second theorem, it states that if we can find the strain energy U given U, which is the strain energy, then the deflection at some point, okay, the deflection at some point where there is a force is given by the derivative of the strain energy with respect to the force P. Okay, this is Castigliano's second theorem. I mean, this is not like the full theorem, but this is the part of the theorem that you should know. Given the strain energy, the deflection at some kind of point where there is a force is given by the partial of U with respect to P. Now let me just give you a quick example of this. Say we have a very simple beam, say it's a cantilever, and we have a force P on the bottom here. We'll say this is L, blah, blah, blah. And we want to find the deflection at this point. Let's call it A. Okay, so what's the deflection at A? Well, let's use Castigliano's theorem. First, we have to calculate the strain energy. And this is another thing that you should memorize. The strain energy for a beam is equal to the integral of the bending moment squared over 2EI dx. Okay, from 0 to L. So the strain energy is equal to the integral from 0 to L of m squared over 2EI. However, this is only considering bending moment. But if you recall, when we make this cut, there's also a shear force, right? And a lot of the times they will tell you to ignore shear effects because they are negligible compared to bending moment. But sometimes, and this might show up, you have to take into account the shear force as well. And when you have to take into account the shear force, you have to add another term here. And this other term is also an integral, but now it's going to be equal to the shear force squared divided by 2GA. Okay, and G is known as the shear modulus, and A is the cross-sectional area, but in the lateral direction. Okay, I and A are two completely different things, two completely different directions. All right, and that's something you should note. If you remember from before when we did the deflection for the unit load method, we had that the deflection was equal to integral of m bar over EI, right? That's only considering bending. If we had to consider shear as well, we would have to add another term, V bar over GA. Okay? Is just an extra term that you have to add. It's an additional computation that you have to make. All right, but you should know that if it doesn't explicitly say consider only bending, you have to consider the rest as well. All right, and for some reason I cannot get rid of this. There we go. Anyways, we'll consider shear for this example because I know we need to get a shear example in. But yeah, so let's do it. Okay. So what are we going to do? We're going to define our axes. We're going to define our axes. This is x-axis going this way. And like I said, we're going to make a cut. This is a very simple cut. We're just going to go like this, and like that, and just like that. And we're going to have a shear force this way and a bending moment. Let's do it that way. So this is M, and that's V, and we have an applied force P. Okay, and this distance is x. Okay, so summing the forces, we see that V is equal to P, and we see that M, when we sum the moments, we see that M is nothing more than Px. Okay, that's the shear and bending moment, and now we plug this into here, so we get that the strain energy is equal to integral from 0 to L of P squared x squared over 2EI dx plus integral from 0 to L of p squared, because v is just p squared over 2ga times dx. Alright? And let's keep going. I'm just going to take the integral. It's going to give us p squared over, so it's L cubed over 3, p squared L cubed over 6ei, plus p squared L over 2ga. Alright, and that's the strain energy. And the last step is that the deflection at point A, this deflection right here, is nothing more than the derivative of the strain energy with respect to the force via Castigliano's theorem. So when taking the derivative, we have a power of 2 here and a power of 2 here. So we can actually factor this out, which I'm going to do, and that's going to give us L cubed over 6ei plus L over 2ga, all multiplied by p squared. Alright, and then the derivative of p squared is just 2p, so this is going to give us 2p times all this garbage. Dun, 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 dun. And that's the answer. That's a deflection at A. Now, this is very useful. This is indeed very useful, and it's another tool in your arsenal. But where this really comes in handy is with this method called the fictitious load method. Fictitious load method. Fictitious load method. So we're basically covering 2 topics in one video here. So it's kind of like a bonus for you, isn't it? Okay. Now, let's go to this example of a beam. That's a short beam. Of a beam, and then it's supported over here, and it's supported over here with rollies. And we have the same distributed load from last video. Okay? We'll call this A, we'll call this B, and we'll call the center C, L over 2, L over 2. And let's say we want to find the deflection at C. Okay, well, we can use the Rayleigh-Ritz method as an approximation. We can use the unit load method. That will work. But let's use Castigliano. Okay, let's use Castigliano. So what we're going to do here is we can't directly use the second theorem because there's no there's no concentrated force, right? Here we had a concentrated force at point A, so we can take the derivative. But here we have a distributed load, correct? So we're going to have to create our own fictitious load. And a fictitious load, fictitious means fake. So we're going to add in this fake force at the point of deflection. We're going to add this fake force, and let's give it a name. We'll call it P. And this, by the way, is Q. Q naught. Okay, and this is what we're going to do. This is exactly what we're going to do. Castigliano's theorem. Remember, it says that the deflection at point C is going to be equal to the derivative of the strain energy with respect to this load. But since this is a fictitious load, it's a fictitious force, it's not actually there. So in fact, we have to modify this a bit, and we have to modify this by saying evaluate this at P equals 0. And then everything works out. It's like magic. So we use the same theorem. The deflection is equal to the derivative of strain energy with respect to load. But since this is a fake load, since it's not real, we have to evaluate it at P equals 0. And I'll show you what we mean when we get on through it. But yeah, so let's do it. As always, we need to find the strain energy. Strain energy from before is equal to integral from 0 to L of m squared over 2ei dx. I'm not going to do strain here because it's just going to get too messy. As before, we have to make 2 cuts. One over here and one over here. Right? And in this case, it doesn't really matter where the x-axis is, but let's just say for our purposes, it starts from the right over here. Because we're going to have to find this reaction RB. But it's fairly simple in this case because it's a determinate system. And what is a determinate system? Well, let me show you. So let me pick a different color here. Let's say orange. So these are the reactions going on here. We have RA and we have RB. Okay, and let's say we want to find these, right? So we're going to do sum of the forces in the y direction. And this is going to give us RA plus RB equals, well, these guys are equal to the force going downwards, correct? And the force going downwards is Q naught times L. Because Q naught is per unit length, so we have to multiply by the total length. So that's one equation. And then to find RB, we can sum the moments about A. And what this will give us, well, this guy is going upwards times this whole distance L and counterclockwise. So it's going to be RB times L. And it's going to be equal to this guy. And since this guy is uniform, since the distributed load is uniform, we know that it acts in the center, exactly in the center. And in the center, its moment arm is L over 2. So the force is Q naught L times L over 2. So that means that RB is nothing more than, this cancels with this, nothing more than Q naught L over 2. Okay? And this kind of makes sense. Since RB is equal to Q naught L over 2, that means RA is equal to Q naught L over 2. And that means that both of them share the same load. And because this whole thing is symmetric, right, it kind of makes sense that they share the same load. And this is what I mean by determinate. Determinate means that you can solve for RA and RB purely from the statics of the situation. This is just statics, right? It's what you learned freshman year. It's just statics. And if you can solve for the reactions using statics, that means that your system is determinate. Okay? But sometimes you can have a situation where the system is not determinate. And as an aside, let me give you an example here. This is a bit of a tangent, but it's pretty important as well. We can have the same setup here with a support here and a roller here. But if we have another support here, then our system is completely indeterminate. It's completely indeterminate. Why do I say that? Well, let's look at it, right? Let's look at it. We have RA here, we have RC here, and we have RB here. Now we have three forces, right? We have RA. If we sum the forces in the y direction, this gives us RA plus RB plus RC equals Q naught L. And if we take the moments around, let's say A, we get RB times L plus RC times L over 2 equals Q naught L squared over 2. You see the problem here, right? We have three unknowns, but only two equations. So this system is indeterminate. Indeterminate. And there are methods of solving indeterminate systems where you replace this with just a regular load and you solve for that load. Okay? And that you can apply any of those methods to solve for indeterminate systems. But that's just an aside on the difference between the two. Anyways, this system we have right here is determinate, thankfully. So we can continue with our progress. We found RB is Q naught L over 2. So now let's make two slices. One here and one here. First slice. We go right here. Boom, boom, boom. We're going to have RB going up, which is Q naught L over 2. And we're going to have this load from over there. And have that load. And that's it. And then we're going to have a bending moment. Let's make it counterclockwise. Okay? So now all we have to do is we solve. So this is Q naught. So sum of the moments about this corner. And what does that give us? First of all, we have plus M from this guy. And then, as always, this distance is X, right? Plus this guy, Q naught L over 2 times X, which is also positive. And then lastly, we have to take care of the distributed load. Now the distributed load from before, since it's symmetric, is going to act exactly in the center, and which means that this distance right here is X over 2. And the actual force the concentrated force, is going to be Q naught times this distance, x, Q naught x. So this is the force, and this is the distance. And we know that it's going clockwise, so we have to subtract Q naught x times x over 2. Okay? The force times the distance gives you the moment. And this is going to be equal to 0. Okay? So from this we solve for m, and m is nothing more than Q naught x squared over 2 minus Q naught L over 2x. Okay? There we go. And now we do the same procedure over here in this cut. So let me just draw it out. We have this guy, and there. And now let's be careful here because we have to add our fictitious force P. We have to add our support RB, which is equal to Q naught L over 2. And we have to add our distributed load. Okay, great. Boom, 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 boom. And of course this distance is x. This distance is L over 2. And I think that's it. Okay, and again we're finding the bending moment. So, same thing again. Sum the moments about this edge equals, we're going to have plus m plus Q naught L over 2 from this guy times x. We're going to have a moment from, so we've taken care of this, we're going to have a moment from P now. So plus P times x minus L over 2, right? X minus L over 2 is this distance right there. And then minus, this is Q naught, and Q naught is acting once again directly in the center here. So minus Q naught times x, which is the force. And then what's the distance here? What is the distance here? This is a little bit more tricky, right? It's not this distance here, it's this distance. And this distance is just half of x, because this guy is symmetric, remember? And so this distance is x, this whole distance is x. So half of it, x over 2. Simple as that. And of course this is equal to 0. This is getting tedious by now, so m is just equal to Q naught x squared over 2 minus Q naught L over 2x minus P times x minus L over 2. Okay, so just to recap, we've used the statics to find the reactions, we've made 2 cuts, and then we followed our normal procedure, finding the moment here, finding the moment here. And now after all of this, we have to find the strain energy by integrating from first 0 to L over 2 of m1 squared over 2ei, and then the second one, L over 2 to L of m2 squared over 2ei dx. And this is going to give blah, 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 blah. But notice very carefully. Take a look here. This is m1. And take a look here. This is m2. Okay? The theorem, Castigliano, the delta at point C is equal to the derivative of the potential with respect to P equals 0. Evaluate at P equals 0. So you see we have a P over here. There is a P over here. So in fact, when we take the integral to find the strain energy, and when we take the derivative and set P equals to 0, this guy will go away. So in fact, the procedure is simple, and this is a valid method to find the deflection. So I'm not going to do it because it's very tedious, but I'm just outlining the steps. And this whole method is called the fictitious load method, okay? So we've covered quite a bit in this video.